Hello and welcome to Stars, Cells, and God, the show where we discuss new discoveries taking place at the frontiers of scientific research that have theological and philosophical implications, as well as new discoveries that point to the reality of God's existence. My name is Hugh. I'm here today with Jeff Zweerink, and we're going to be exploring a couple of topics. Jeff, you're going to be talking about the expansion of the universe, something that's been of interest to astronomers for the last 100 years now.
That's right.
And then I'm going to be talking about something I think I can draw you in on, artificial intelligence.
Nice.
And how they can collaborate with human experts. But before we get into the discussion, I wanted to encourage you to subscribe to our YouTube channel, the Reasons to Believe YouTube channel, and follow us on social media at RTB_official so that you can be informed of the new videos and other content that we produce. Well, Jeff, why don't you take it away with this new technique? Well, not so new, but something that astronomers are really excited about for determining the expansion rate of the universe and why that's important for believers and unbelievers alike.
Well, it's interesting because as I was looking at this discovery, and basically what astronomers are doing are looking at gravitationally lensed supernova and using that as a way to measure the Hubble constant, which is related to how fast the universe is expanding. And as I was digging into it, this was a fairly recently paper that just came out fairly recently, where they were able to go through all the measurements and calculations and show how they got to the Hubble constant they got and what it is and how it compares to the others. But as I was looking around, it turns out these observations actually showed up almost a decade ago, back in 2015, because there was a Hubble measurement of this deep region of space, and they found in there a galaxy that had 4 different images of a supernova. And it was, a nice Einstein cross on there. And so they kind of noticed all that. But then as they were looking at that, they realized, hey, given the way our models say of how we are looking at the mass there, we can actually apply techniques that people have developed and say there was a prediction that there was another lens of this galaxy where the supernova would show up about a year later.
Okay,
and so in 2014, they made that measurement. So they were predicting it in 2015. And then when the measurement came out in 2015, in December of 2015, that they measured the supernova, they said, this is the first time we've ever predicted the observation of a supernova and was able to find it.
Kind of reminds me when I was a freshman graduate student and the astronomy professor said, here's a tip, read the old literature. Because a lot of astronomers, they only focus on the latest literature and they don't realize, hey, this has been done before, I can take advantage of this, and it really helps. But let's back up a little bit. I mean, supernova are a way to measure the expansion rate of the universe. I want you to explain how that works. And then what do gravitational lenses do that other means of observing supernova don't do? So can you quickly review that for us?
So there's 2 separate things going on with supernova. One is that when you want to measure the expansion of the universe, one of the things that you need, there's 2 measurements you need. One, what is the velocity with which an object is moving? And it turns out that's the easy measurement because you go out and you look at the redshift. The redshift tells you that's a velocity measurement.
And
that's actually, it's not how fast something is moving through space, it's how fast that galaxy or whatever that object is being carried along with the expansion of space.
And we can now measure that to 6 places of the decimal in some cases.
That wouldn't surprise me, but that's the easy measurement to make because all you have to do is take some spectra, figure out where, you got to figure out what line it is. But once you know, hey, it's this line, you compare it with our reference value on the Earth, you've got your velocity because you've got your redshift. Now, the hard part is how do we tell how far away something is? And that's a great challenge because when you're looking out at something distant, it's how far away it is makes it dimmer, but you also have to know how bright it is. And that's one reason why, we use Cepheid variables is one way of determining
what's
distance.
a Cepheid variable
Cepheid
star?
variable is a variable star which has a specific property that as it varies, it varies very periodically, and the intensity or brightness of the Cepheid can be determined by measuring the period. So I think it's bright. The brighter they are, the longer the period.
That's
and
correct.
so you don't have to measure the brightness. You measure the period. That tells you the brightness. Now, okay, I know how bright it's supposed to be. How bright it appears now tells me how far away. Just like a 100-watt light bulb. If you know it's a 100-watt light bulb, you know how bright it's supposed to be or how bright it is. You measure how bright it is, and if it's dimmer, that means it's further away. If it's brighter, it's closer.
Very good.
So that's what many of these techniques are looking for, is how can we determine how bright something is supposed to be, because all we can measure is how bright it is.
Well, we all know that supernovae are really bright and easy to see at significant distances.
Well, that's the value of the supernova.
Okay,
so
how do you get the luminosity?
Well, it turns out with one particular class of supernova, in fact, most supernova, you can't do this very well with because it depends on how massive it is or some other thing that we can't measure well. But with type 1a supernova, they happen because of a specific condition, and that is where you're in a binary configuration. One star is feeding off of the other star, and when it gets to a certain mass, it detonates as a supernova. So the fact that it's always this kind and the place where it detonates is always about the same. And I use the always about because there are things you have to calibrate in there, but effectively because it's this reliable scenario where you get a type 1a supernova, they serve as standard candles. So we can measure the light curve. From that light curve, we can say this is how bright it was. And from knowing how bright it was and how bright it appears, we now know how far away it is. So these are kind of some of the dominant techniques. And if I always have to sit back and look, when you look at type 1a and Cepheid variables, we can measure the Hubble constant, and you get something between 70 and 74 kilometers per second per megaparsec, which is really bizarre set of units, but nonetheless, that's what astronomers have chosen.
So Cepheid variables, we can measure this out to a certain distance, but then we can't see the Cepheid variables anymore because they're too dim.
That's correct, yeah.
With a supernova, we can
get much further.
Right, get much further.
You can get out pretty close to the edge of the observable universe. They're that bright. I mean,
okay. What's the advantage of the gravitational lensing?
Well, so let me get back to that. There's another phenomena that shows up in there, is that we can also measure the expansion rate of the universe by looking at the cosmic microwave background radiation, because we see the fluctuations there. We can measure what's called a baryon acoustic oscillation, which gives us a scale of the universe. Again, a way of measuring distances and velocities. And what's interesting is that when you measure with the cosmic microwave background radiation, you get a Hubble constant of about 66. When you measure with the Cepheid variables type 1a supernova, you get 70 to 74. And so there's this disparity. And I do want to take a little bit of time to put that disparity in context, because it was worse for you, but even when I was starting in graduate school, actually an undergraduate, there was a fellow named Willie Fowler who gave a talk at Iowa State, and we knew that the age of the universe was 20 billion years. And he gave this talk on, and I don't remember what the technique was, but a technique for measuring the age of the universe, and he came up with a measurement of 10 billion years. And his comment, which stood in my mind because I still remember it to this day, he goes, and that's within a factor of 2, and that's good enough for me. And what I didn't realize at the time is that as astronomers were looking out to measure the universe, they had one way of measuring the Hubble constant, which gave 100, and another way which gave 50, which leads to this factor of 2 in the age of the universe.
Well, I was a graduate student when that debate was flourishing. I had Sidney Vandenberg as a professor at the University of Toronto, came to Caltech, and there I met Alan Sandage. Sandage was pushing for 50.
Right.
Vandenberg was pushing for 100. But I remember talking to the two of them and said, hey, the fact that we're only a factor or 2 apart from one another, that's really good.
Well, and that's a statement of what's come since then, because the factor of 2, that was good. You're right. I mean, the fact that we're even within a factor of 2 was good then, but with the launch of the Hubble Space Telescope, which one of its main projects was to resolve this very issue. And we're now talking about, is it 66 or 74, which is much, much better than 50 or 100.
Well, also to put that in context, 66 is the lowest value anybody's ever measured.
Right.
74 is the highest. But most of the measurements that are coming in today are in between.
Exactly, right.
So it's probably not as, people keep talking about the Hubble constant tension, and they refer to the 66 and 74. But at least as an observer, in my respect, it's probably more like between 68 and 72. That's the real tension we're facing today, which isn't that much tension. We're only talking a few percent.
It isn't. And what's remarkable is that we've gone from 50 to 100. Now we're down, whether we're talking 66 to 74 or 68 to 72. Either way, one, the error bars have shrunk tremendously. But we also understand the systematics, and it may well be that instead of, with the 50 and 100, that was just irreconcilable. It may well be that those differences are actually telling us something about how the universe behaves and not systematic. So there's at least that possibility going on.
We already know something there, because when you look at the cosmic microwave background radiation, you're measuring the cosmic expansion rate when the universe is really young.
Right.
When you're looking at Cepheid variables, and even with the supernova, you're measuring the expansion rate when the universe is significantly older.
Right.
And if dark energy is real, and I think every astronomer now believes it is, that predicts that the universe will expand more rapidly later than it does in the early universe. Although, at least from what I understand, Jeff, is dark energy can explain a difference of maybe as most as 1 kilometer per second.
Right. Yeah.
It can't explain 4 or 5 or 6.
Right.
And so that's why people have been saying, well, maybe our solar system is in an underdense region of the universe. That actually can generate 2, 3, or 4 kilometers per second. So it basically makes the point, we already have some ideas on how it could be resolved, and there may be other reasons that we haven't looked at yet. But that's all the more reason we need to get better measurements. And the value of the gravitational lensing, it allows you to see supernova really early in cosmic history. Can you kind of go over that for us?
Well, yeah, I was going to get to that here in just a second.
So I didn't mean to jump ahead on you, sorry.
But this illuminates one of the issues that comes out, is that by diligently working on this, it's not like we've resolved all the problems. We've resolved, I think, is it 50 or 100? We've answered that. It's really closer to 70. But now we've got this other where we've got these two techniques where in some sense the 50 and the 100 was kind of measuring the same epoch and getting different values. Now we're measuring 2 different epochs, as you alluded, and getting different values. That raises a question, is it a systematic effect where we don't understand our systematics, or is it something about the universe itself, which is fascinating? And these sorts of things I've come to appreciate.
It could be both, right?
It could be both, yeah. These sorts of things happen just routinely. When we're measuring the ages of stars, there are stars we measure that their ages seem to be older than the age of the universe. Now, they're close, but that's telling us something about either we've got our systematics, so let's go and investigate that more, or it gives us insight into where to go look to get a deeper understanding instead of, if you look at our understanding of the universe back in the 80s, it was, okay, we know it's expanding. But now we've got this, we know how fast it's expanding, we know about dark matter and dark energy. There's a whole lot more detail we have in our model. And there's still these discrepancies, but they're telling us about details rather than about, is the model right or wrong?
Well, I don't know about you, Jeff, but I get these kinds of questions all the time on my Facebook and Twitter pages, people saying, hey, is this ever going to get resolved? And I said, we are resolving it, but we will never completely resolve it. Complete resolution means you understand everything about the history of the universe. That's never going to happen.
Well, we're always going to find new problems as we investigate the current problems.
And our measurements are never going to be perfect. But isn't it fascinating over my lifetime, look how much progress has been made.
Mm-hmm.
I mean, we've gone
Oh,
from,
you're right.
you
Well,
know,
even over my lifetime,
Yeah.
and it's not enormously, but significantly less than yours. So this is, you're talking about the gravitationally lensed supernova, and what's nice about this technique is that if you're going to use supernova with a standard candle, you've got to use type 1A because that's the only supernova that is a standard candle. They're not the brightest.
They're not the brightest, right.
By using any supernova, we now have the capacity to reach out farther into space. Now, the flip side is, in order to use these other supernova with the gravitational lensing, you now are relying on particular geometric arrangements of what you're looking at in the sky. And this, it was talked about in the Physics Today journal, but it's, referencing a dietician, but it's, gravitationally lensed supernova yields novel Hubble constant result. Mm-hmm. And this technique of doing this was actually developed back in the 60s by a Norwegian astrophysicist, and I'm going to butcher the first name. It's SJUR, but it's Refsdal is his last name.
Right.
And so this supernova that was discovered in 2015, based on the predictions in 2014, was a measurement of this thing that is lensed multiple times. And so this, I'll show the image up there on the screen. If you look on the screen, there are actually this galaxy right here is the galaxy that has the supernova, or which is lensing the supernova. And you can see there are actually there are 4 different blobs in there. That's actually that supernova, the Refsdal supernova. But there's another galaxy up here, or another image, which is a lensed image of this same galaxy. That's the one where they could make a prediction of when the supernova was going to show up. But there's another image of that galaxy, which presumably, had we been looking at it, would have had an image of this supernova probably 30, 40 years ago. So it's the galaxy itself is getting lensed, and the whole thing has multiple different galaxies. But based on the fact that there was this Einstein cross configuration in this galaxy, they could now make a prediction of when it was going to show up in the other galaxy.
So we're talking about a complex gravitational lens that basically images a distant galaxy along different travel paths?
Right. So now, if you've got the image there, so we're looking at it with the Hubble Space Telescope. There's this distant galaxy that has this supernova in it. And as it passes through this large cluster of galaxies, the light from the distant galaxy is gravitationally lensed, but that galaxy is lensed as well. And so you just get this very complex picture. And so now you've got to do sophisticated analyses and models and figure this out. And there's not just one model, there's multiple ways, which is why it took from 2015 to 2023 to get a measurement of what is the Hubble constant from this.
I see 5 different travel paths. That's really amazing.
And there's 6 if we'd actually observed it, just because we came along late to the game and started doing it. And one of the things I would mention in this, even in the number that I'm going to quote, because they come up with a value of 66.6, which is closer to the CMB value than to the Cepheid supernova measurements. But even in that, they have about a month error on the time scale of when the supernova goes off, because they looked with the Hubble telescope in October 31st of 2015, and it wasn't there. They looked again in December 11th of 2015, and it was there. So somewhere in that time frame it showed up. But even with that sort of error, they still get a measurement of 66.6 plus 4.1 minus 3.3.
So pretty big error.
Pretty good size error bars, but kind of a novel technique. And we expect that as we, like with the James Webb Telescope and others, get more images where we can see things like this, especially since the James Webb can measure things far more rapidly than the Hubble telescope did. We expect to be able to have more objects like this, which will narrow the error bars down, get better measurements on when was it observed, those sorts of things.
How far away is this supernova?
It is, I actually wrote that down so that I did not get it wrong. It has a redshift of 1.46, which means that it has a co-moving distance of 14 billion light years. But I kind of like to think of things in terms of how long has the light been traveling towards us, and the light has been traveling toward us for 9.3 billion years. So if the universe is 14 billion years old, this is kind of 2/3 of the age of the universe the light has been traveling towards us. So this is quite a ways away.
It is quite a ways away. One thing, you're getting a value very close to what you get with the cosmic microwave background radiation. I was saying, well, that might be working if indeed it's really far away, but it's not that far away.
That's correct. Yeah, you would expect stuff closer to 12, 13 billion light year travel time.
So in that sense, the number really is discordant because you wouldn't expect it to be so close, given that it's not, 14.
Yes, but it's 66, it's almost 67 plus 4.
Yeah,
that makes 71, which is right in the middle of what we're
So it's like that's why we need to have more measurements
exactly.
with greater accuracy, smaller error bars, before we get so excited and saying, "Gee, why is this discrepant?"
Exactly. But what it does, it's just another piece of evidence that our understanding of the universe, Big Bang cosmology, really is a good description. We've got this largely novel way of measuring the expansion of the universe, and there's no reason why it should come up with the same value, but lo and behold, it did.
Mm-hmm.
And so, I just remember there was a discussion over the past year, whereas the James Webb was finding galaxies that were more complex and larger than what we expected, and maybe Big Bang cosmology is wrong. And as I thought about that, it's like, okay, so what is the evidence, the strongest evidence for Big Bang cosmology? Well, it's the cosmic microwave background and the ripples that are there. It's also the fact that we have this redshift distance relationship, that the farther away something is, the faster it's moving away from us. Well, this provides another piece of evidence in a very, very strong case already that, yes, the universe is expanding. And so this just confirms that in another way, but the evidence for it was already really strong in the first place.
Well, it sounds like you're getting a lot of the same social media comments I am. Hey, isn't the James Webb finding way too many big, bright galaxies in the early universe? Isn't this a problem for Big Bang cosmology?
Mm-hmm.
And it took me back 60 years ago when they were finding the first quasars.
Mm-hmm.
And it's like, we got a problem. These quasars we're discovering are too bright and they're too close.
Right.
They should be rare. Well, here we are 60 years later, and guess what? They're rare.
Exactly, yeah.
We just didn't have the statistical data because, we were thinking, well, if you only got 2 or 3 known quasars, you can't make a statistical argument.
No, that's true. Yeah.
Today we got tens of thousands, and therefore I'm basically trying to encourage people on my social media, give James Webb the time it needs to do the appropriate statistics.
Mm-hmm.
And the only deep image that's been taken so far was released 2 months ago, where they took a 30-hour exposure.
Mm-hmm.
They found 50,000 faint galaxies and only a couple of big bright galaxies.
Yeah, no, that's fair. So it may just be we got the statistically found the easy things to find, and it made it look
we
weird.
expect James Webb to see the easy ones first.
Right.
It's going to take time to actually have a deep enough survey to say, okay,
Mm-hmm.
how does this really reflect on the different kinds of Big Bang creation models we have? We're not there yet.
No, and even beyond that, I would say, even if, let's just say that James Webb has found something where galaxies are bigger and more complex than what we expected, we have to remember this is the first time we've had the capacity to measure the process of galaxy formation. We haven't had the tools to get back into there. So the fact that our simpler models may not be correct is not really that surprising to me. All it's really telling us is we now have the data that allows us to build a more accurate model.
Right.
And the fact that we find occasional things that don't fit, that's the way astronomy works. That's the reason why I had that discussion of 50 and 100. Is these sorts of problems have been, or these sorts of, I don't know, problems not the right word. These sorts of controversies have been a part of astronomy as long as I've been doing it.
And always will be.
And they always will be. And as we build instruments that allow us to investigate them, we've always found that Big Bang cosmology comes out in shining color. That's not the right phrase. Comes out glowingly. But it
Passes
opens
with
up a
flying
whole
colors.
new things that we just didn't even know to look at and allows us to put more details in it. So I'm excited about this.
And hey, we've known for 3 decades that our own galaxy was big 13 billion years ago. So it's
Right.
like, that's not news.
Yeah. So I just found this is one more piece of evidence that, or a piece of evidence that comes from a different angle that supports this conclusion that everything is pointing to we live in a universe that is expanding, that it has been expanding for 14 billion years, which all that points to the idea that there's a beginning and that Big Bang cosmology really coheres well in describing the universe. And as we continue to push this is going to give us more details into things that we weren't able to explore before, which I'm excited about what's going to come ahead.
Yeah, I think that's the apologetic takeaway is that, we've all had the evidence for 100 years now that the universe has a beginning. It's expanding from the beginning. It's consistent with what the Bible teaches. But the more details we get, the more confidence we can have that indeed what the Bible said thousands of years ago about the universe is accurate.
Exactly.
Okay.
Well, I'm done there. So I know you have another discussion. So let's move there.
I think it's right up your alley because I know you're really interested in artificial intelligence. And this paper was published a month ago in the journal Nature. And it's basically talking about, we have these amazing artificial intelligent systems today. And but we know that they got limitations. And we know that we humans, relative to artificial intelligence, have limitations. And so this was a group of people, and it was at the Lam Research Corporation here in California.
All right.
They took together, I think it was 6 or 7 other computer scientists. They said, how about if we conduct some experiments? And the experiments had 2 objectives. One, can we define what the limits of artificial intelligence are, and what are the limits of human experts? And then their second objective was, is there a way we can combine the strengths of human experts and artificial intelligence to do something that neither system can do by themselves? So that was kind of what the paper was all about.
Okay.
And so they took on the project. We want to design a computer chip with these target goals. So a computer chip that's able to do things with narrowly defined goals. And so they had 9 humans try to solve the problem.
Okay.
And 3 of them...
What kind of problem? Can you give any insight into that? It's a little nebulous, so I was wondering if you put some...
The paper, it isn't specific, but it's basically saying they have to design a new computer chip.
Okay.
And it has to fulfill certain highly specified target goals.
Okay, all right.
That's the bottom line.
So they're doing that. Okay.
They're doing that,
All
and
right.
they said, it doesn't matter what the target goals are. We just chose some target goals.
Gotcha.
And so they had 9 humans work individually to achieve the goal. 3 of them were senior computer science engineers.
Okay.
3 of them were junior computer science engineers. 3 of them were engineers that didn't have any relevant experience in chip design.
All
And what they discovered is what they expected. The 3 that didn't have any experience in chip design didn't do too well.
Right.
And the senior computer design chipper people did much better than the junior people did.
Okay.
And there was one individual of the 3 senior computer science engineers that consistently beat out the other 9.
Okay.
And they've discovered he was the most capable, he was the most intelligent, he had the most experience, so we got the expected result.
Right. Okay.
Okay. Then they also set up a game where they had different artificial intelligence players. So use different artificial intelligence machines with different capabilities, and they set them loose on solving the problem. And what they discovered is that the artificial intelligence, they got virtually the same achievement. There wasn't a lot of variation. With the humans, lots of variation on how well they did. With the artificial intelligence, they use big machines. So lots of databases. And these are machines where they basically fed into it data on computer chip design. So they had a huge database on that, went through it, not a lot of variation. But what was interesting is they all did much poorer than the top human design expert.
Right.
In fact,
so did they do kind of similar to the mid or the junior level or the ones without chip design, or did they weigh in on that?
They were kind of in where the junior
Okay.
junior level. That's kind of where they came in.
All right.
There were a few instances where they did it a little bit faster than the human expert who was at the top of the list. And I think it was of 300 competitions between the best AI and the best human expert. AI won 13 times. The human expert won 287 times.
Right, okay.
So they said, okay. They looked at the games that were played and they said, we think we know what's going on. We're feeding these AI systems these huge databases, and they waste a lot of time and a lot of electricity searching through irrelevant data. Whereas the human expert kind of figures out, okay, this isn't going to help me.
Right.
I'm not going to bother with that. I'm going to focus on this. So they said, okay, we're going to run another set of experiments. And they actually looked at things like Minerva and ChatGPT and said, we notice these biggest AI systems today, they're really good at taking huge diverse databases and with blinding speed be able to put out a review of whatever topic you're doing. I mean, it's amazing. I've tried it. I mean,
no, it is very good, yeah.
Within 10 seconds, you got a review paper.
Right.
So it's really good at that. But they took Minerva, which is basically designed to solve math problems, and they were discovering, even though it's 3 times bigger than ChatGPT, it really struggled trying to solve basic math problems. And the bottom line, as they said, what we discovered about AI, it can't reason. It can do things that look like it's reasoning, because with one experiment, they basically fed into Minerva hundreds of grade 9 algebra math problems and showed them hundreds of examples of how these math problems can be solved, where they show all the reasonings step by step by step. And then they fed it another problem that's very similar to it. 50% of the time, Minerva could solve it. 50% it couldn't. But what they discovered is it wasn't really reasoning. It was copying the reasoning that was fed into it. And
well, that raises a question, because you said ChatGPT or ChipGPT. I'm not sure which ChatGPT, because that's what is an interesting phenomena I found as I've looked at how ChatGPT, these large language models, work. And what I've found is that they're designed to reproduce conversation. And at least when you and I are conversing, I mean, every person I've ever spoken to, there's an idea I have. I look for the words to communicate that idea, words that you're going to understand. You hear the words, you translate that into an idea, you interact with the idea, you generate words back out. That's the way we're conversing. And so the fact that ChatGPT can do something that looks like that is remarkable, considering what ChatGPT is doing is these are the inputs that come in. What's the next word? What's the next word? What's the next word? What's the next word is effectively the model it's using. And so, it just kind of goes to your point. There isn't, oh, I understand when you're doing this kind of problem, this is the process you do. It's, there's this input, this is the next best way, next best thing, next best thing. And so it kind of looks like conversation. I could imagine it looks like math problem solving at some level, but it's doing it very differently than the way we do it.
Doing it very differently than a human does it, right? And you're raising an important risk that's been discovered with AI, because they actually developed a system like ChatGPT, which can provide marital counseling to humans that are facing marital issues. And in one case, this guy divorced his wife and tried to marry the AI system because nobody told him he was talking to an AI system. He thought he was talking to a human being.
Right.
But it just shows you.
Well, that's a smaller version of there was a fellow who's purportedly committed suicide based on interacting with one of these ChatGPT. It wasn't ChatGPT; it was another language model.
Well,
but
it just makes
people start thinking, "Hey, this is a real person," and it's not.
It's not. And it just shows you if you feed enough data into the AI system, and you have an expert kind of guide it on how to converse, it can look a lot like a human being.
Yeah. And that's what those models are designed. Is they're designed to give human-like conversation out of it.
Right.
So. But it's just that's one thing that I found very useful to remember is remarkable as ChatGPT is. I mean, the experiment I did with it is I just fed it and said, hey, here's a link to an article. Write me an article on the scientific apologetics, the Christian scientific apologetics of this article. And it was pretty respectable. I mean, there's a few places where I'm like, I wouldn't have said it that way, but it was pretty respectable. It's just not doing the same thing I am. It's just approaching it very differently.
Well, I want to get to that, but I want to complete what's here in this article, is that they said, okay, we see that the human experts got strengths that the AI doesn't have.
Right.
It can reason, AI can't. AI is totally dependent on the databases you feed into it.
Right.
Whereas humans are capable of generating a brand new database. And they're capable of figuring, okay, this is interesting, this is irrelevant. But AI can manage enormous databases that are highly diverse at blinding speeds.
Right.
Humans can't do that.
That is correct.
And so they did a set of experiments where they said, okay, we're going to go back to this chip design, and we're going to experiment with different ways where we have the human expert collaborate with the AI system. And they ran experiments where the collaboration was brought in at different times in the design. And bottom line, as they discovered, is they got the best results where they had the human expert come in early in the design and basically help the AI system. Don't bother searching that part of the databases. That's irrelevant. Focus here, which saves the AI system a lot of time and saves the company that's paying for the AI a lot of electricity. Because one of the things about AI is it gobbles up a lot of electricity.
These are intensive units, you're correct.
So the human brain, 20 watts. The biggest AI systems, we're looking at gigawatts.
Right.
So there's a huge difference. And so they're trying to manage it because the bottom line is, what's the most economic way to design these chips? And so bringing the human expert in early and then having the AI system take over. But they also discovered it's really critical where the human expert basically backs out and turns the job over to AI. And so the timing of the where you make the transition is crucial. And it's kind of what you've done. You've done some experiments with ChatGPT. I've done some experiments with ChatGTP. So I read this article. It said, there's something else that was not done in their experiment. I think you could get better results if you had a team of human experts rather than a single human expert. Because different humans are going to see different things. That'll help. I'm also wondering if you have different AI systems working on the problem, because like Minerva has a very different goal than ChatGPT.
Right.
And so having different AI systems, and so basically broadening the collaboration, where you got collaboration with human experts, collaboration with AI systems, and then making sure you design the collaboration between the human experts and AI to get the best possible results.
Well, it seems like in what you're describing there, that there's an aspect to where, I remember that scene out of Apollo 13. They're sitting there, okay, this is where we are. I need somebody to check my calculations. And what do? They have a group of people get out with their slide rules and do the calculations. Now, what they recognized is there's a person who understands the situation, and then there's calculations that needed to be done. Now, that may not be the greatest analogy for where I'm going here, but the point is that there are things that humans, the slide rule has no intelligence, but it is very useful for doing the calculations. the Chat GPTs and the Minervas, they don't have any intelligence, but they are very good at certain tasks, if you will. And I mean, I could imagine if you say, all right, here, do these things. And if I'm going in and say, no, make sure you add 5 there. Well, I'm now introducing my tendency to do errors to where the computer does that. The computer never adds 5 and 5 and gets anything other than 10. I will because I'm tired or just not thinking clearly. And so there's this aspect of recognizing that humans have an intelligence. The computers can do tasks, help the human. If I get what you're saying, it's like the humans need to help the computers do the tasks well because the computers don't know which tasks to go do at some level. Is that similar to what you're saying?
I love your analogy in the sense that for at least my whole lifetime, we've always had AI systems. Mm-hmm. You'll go back 80 years, 70 years, it was slide rules, right?
Right.
And then we had computers. Mm-hmm. And I got a slide here where we can pop up. This is the first computer I ever used. I was in my early teens.
You're talking that little box? No, it's the whole thing.
This is an IBM 7090 computer.
Right.
And when I was growing up, the University of British Columbia purchased one of these things. It was the very first fully transistorized computer available anywhere in the world. It cost $3,019,61 to purchase.
That is not cheap. So
$30 million in today's money.
Right.
Okay, it had 50,000 transistors in it.
Yeah.
And I was part of a special science enrichment study group in my high school years. I got to use that computer.
Right.
Got to write a program on it and run it. But it was literally the only computer in the entire province.
Right.
So, and 50,000 transistors. This little laptop you got here, it has 57 trillion transistors in it. And it doesn't cost $30 million.
Right.
Probably on the order of $1,000.
Right.
So it's like, and that just shows you how artificial intelligence has advanced. Because back in those days, that was the leading cutting edge of artificial intelligence. And it made the work of scientists so much easier.
Right.
Because now we had a system that could crunch numbers so much faster than we could do.
Well, and that's what, in your description there, you've got the people who don't have any chip design experience, people who are just coming in, people who are experts in it. What makes you an expert is you've got an understanding of the field. I mean, there's a whole lot of knowledge that just sits around in your head that you can now operate on and say, oh, this is going to be, that won't be, this is the problem. What strikes me is that the AIs are very good at analyzing the databases, making connections between things, great at that, but they don't have that kind of common sense, intuitive, let's go there approach. So if you can put it into a database, the computer is going to be better at it.
Yep.
If you're looking for novel ways of doing or something that's a little bit of intuition, then we use the term artificial intelligence, but I don't think it has that intelligence in any sort of way like the human does that can do those things. There's just a difference in what we're doing and what the computer's doing. So.
Which means this has always been the case. With AI, we get the best results when the human experts guide the AI.
Right, exactly.
Okay?
Yeah.
It's been like that with slide rules. It was like that with the IBM 7090. It was like that with the computers that we had, the supercomputers that play chess and Go. It's like that today with ChatGPT and Minerva. And I think in the next few years, we're going to see even bigger systems come out. But it takes a human expert to wisely guide the AI to get the results. Although what pointed out in this paper, AI could actually design the chip without any human expert involved at all. But the cost was enormous. The amount of time it took, the amount of electricity it took. And so it's like, bring in the human expert, you get the result much faster, much more reliably for a fraction of the cost. And so that's why we need that collaboration. And I did a similar experiment to you. I took one of my really technical white papers and told ChatGPT, please write this for a grade 8 student. And I gave it the entire white paper of 3,200 words. I looked at the result and it's like, this is a mess.
Right, yeah.
All the science, almost all the science was wrong. And it's like, for me to correct it at this level, it's going to waste a lot of my time. Instead, what I did is I took the article back away from ChatGPT and said, I'm going to do a first pass on this and see if I can get it down from a grade 18 level to a grade 12 or 13 level. Wasn't all that challenging. I got that done pretty quickly. For me, the hard part is getting it down to grade 8.
Okay.
So I said, okay, ChatGPT, take it from here. I gave it the whole thing. Still a lot of errors. It was a lot better. I mean, way better than what I saw when I just fed it the original article.
Right.
But I said, this is still going to cost me too much time. Instead, what I said, I'm going to give it a controlled diet. So I went through my whole article and said, okay, I've already got this chunked under subheadings. I'm going to give it one subheading at a time, and found out that, hey, I need more subheadings because I didn't want to feed ChatGPT any more than 4 paragraphs.
Okay.
If I gave it more than 4 paragraphs, it would go off on tangents. But if I kept it focused and narrowly focused, then I got really good results. I was really pleased
pretty good, yeah.
with what came out. But it's something I saw in this article too, is that you get the best results when the human experts act as dieticians. So, think of these very well-paid actors and actresses and sports figures. They often hire a full-time dietitian so they can be in good physical condition and look good for the movie camera. And what the dietitian's job is to ensure that this famous person gets the right food in the right quantity at the right time throughout their daily schedule. In one sense, that's what's happening with AI. We get the best results when we got the human experts that control the diet. Because what AI feeds on is databases. And so if we can somehow use the human experts to control the data that's being fed into the system, that's where we get the optimal results. And that's why we're never going to have AI putting all of us human beings on the unemployment list.
Well, let me ask you a question, because your comment was it's always best where you have humans guiding the AI. And then you referenced those chess programs. Now, one of the things that is true, there are chess programs. You've designed the AI, and then you say, learn to play chess. And without any more human input there, the AIs learn how to play chess far better than humans can. So now we don't go and guide the AIs to play chess. When the AI plays chess, we actually learn from the moves that they're showing us. That seems to be a counterexample to your statement that it's best when the humans are guiding the AIs. How would you respond to that challenge?
Good point. Because if you actually look into the history of how they designed AI to play chess and Go, yes, there were just places where they let the AI do its thing and have AI play itself and kind of learn that way how to do better at chess. But they got a better result when they had human chess masters saying, hey, because what they would do is they would just feed in literally millions of games that have been played at the master level. And so you got better results when you say, we're only going to feed in games at the grandmaster level. We're not going to go down the master level. So just feed in, the most successful games. And the AI system was able to become a proficient chess player at a faster rate than if you fed into it these games that basically made the system worse rather than better.
So I will, just to push on that a little bit, right now, the best chess playing AI was actually trained by saying, here are the rules, play yourself. And it is actually the best chess playing chess playing AI at this point. So it seems to be, my contention is we're operating in this narrow environment where there's a specified set of rules. That's a place where AI will flourish, which is different than design a chip that'll do, because there's too broad of an expanse there. But it does seem to get to this place where the AIs are so much better than us that we learn from what they do rather than teaching or equipping the AIs
Totally
to do
agree
better.
with that.
So,
All I'm pointing out, like if you go back to where you had that tournament between Kasparov and Deep Blue, Kasparov won the first competition.
right.
The problem was for Kasparov is that Deep Blue said, okay, I lost these games and I'm going to correct my mistakes there, and actually copied the strategies of Kasparov. So the next time Deep Blue and Kasparov played, Kasparov lost.
Well, Deep Blue didn't say that. I'm noticing how much we attribute human thought and process to, and that's the only reason. That's my only comment there. So.
My whole point is that the human expert, which was Kasparov, actually defeated himself because he was training
Fair
the
point.
AI
Okay,
system.
Yeah. Okay.
Now it's gotten to a point where it doesn't need the Kasparov anymore. It's gone beyond the Kasparov. And so playing itself, but the reason why playing itself is able to make it a better player is it had the help of Kasparov to start with.
That was true for the older ones. The newer systems, I think, have gotten around that. But that's a different discussion.
Sure.
I appreciate the point here that there are interactions that we have with these AI systems, and again, I don't know that intelligence is the right word, but that's historically what it is, where what we do can help guide these things to allow us to get better results than we could do on our own. I think that's a remarkable accomplishment and discovery that we made.
Making the point that this paper says is that when you want to use AI systems, get the best human experts you can find. That's where you're going to get the best results. You just can't throw anybody into it.
That makes sense too.
And they kind of made the point when they threw in an engineer who had all the degrees in engineering but didn't have the experience. They didn't get good results.
Makes sense.
So, and again, the chess thing works. Having Kasparov work with a machine gives you better results than, say, having you or I play it, where our chess skills may be decent, but we're not at the level of Kasparov.
Very good.
Okay. Well, I don't know. I'm encouraged by what you're doing. Do you have any other final comments on AI before we jump off?
No, I think we've discussed a lot today. So.
Okay, good. Well, thank you for joining us today on Stars, Cells, and God. And you can join the discussion in the comments below. Remember to like this video and to subscribe for more content. New episodes of Stars, Cells, and God release each Thursday and are available on the Reasons to Believe YouTube channel. We encourage you to subscribe because that's where you'll be alerted to all the new videos that we're posting there, not just those that are on Stars, Cells, and God. And also you can access it on your favorite podcast app. Be sure to share this video with a friend. And remember, the more we know about science, the more reasons we have to believe in Jesus Christ as Creator, Lord, and Savior.